Hello, I'm Philipp and I will give you a summary of our workshop paper, CANDID DAC, Leveraging Coupled Action Dimensions with Importance Differences in Dynamic Algorithm Configuration. This was joint work with Hasan, Eddie, Noor and André. In dynamic algorithm configuration, we aim at learning to adjust the hyperparameters of an algorithm throughout its execution. For this, we employ reinforcement learning. And in this paper, we address one of the key challenges of RL in DAC, the structure of the action space. So let's have a look at what makes DAC action spaces challenging by the example of neural network training. Here we need to set a variety of hyperparameters. And if we look at the resulting action space for DAC, we see it is high dimensional as we have to set so many hyperparameters. There are interaction effects between these action dimensions. Setting one hyperparameter affects the optimal setting of others. But there's also a property of these action spaces that we can exploit. From prior work we know that some hyperparameters are more important than others. There are different approaches to learn in high-dimensional action spaces. For once, we can learn a single policy that sets the values of all hyperparameters. However, this approach scales poorly with their number. As an upside, it searches over the joint action space and can handle interaction effects. Other prior work has learned a policy per hyperparameter to avoid combinatorial explosion of the action space. But while these policies can be trained jointly, they can only condition the actions on the current algorithm state and are limited in handling interaction effects. We propose to employ sequential policies. In this approach, we still learn a policy per action dimension or hyperparameter, but we select the hyperparameters in a sequential process, starting with the most important one. Subsequent action choices are then made based on already set hyperparameters. By learning a policy per action dimension, we still avoid combinatorial explosion. And by conditioning on the already set hyperparameters, we can learn about interaction effects between them. In order to answer the question whether sequential policies are suitable to learn coordination over many coupled action dimensions, we defined the piecewise linear toy benchmark. It builds on the Sigmoid benchmark that was introduced in prior work. It was designed to investigate the ability of RL algorithms to scale with the number of action dimensions. Our new benchmark adds interaction effects and importance differences between the action dimensions while still allowing to scale their number. This is illustrated by the comparison of the reward surfaces at different time steps. Here we see that action dimensions can be optimized independently in the Sigmoid benchmark, but this is not possible for the piecewise linear benchmark due to interaction effects. We ran several experiments on this new benchmark and compared different DeepQ network-based policies. In the upper row of the plot, we varied the number of action dimensions and kept the number of action choices per dimension fixed. In the bottom row, vice versa. Increasing the number of action dimensions increases the number of policies to learn in the factorized and sequential setting. In these experiments, we observed that sequential policies are indeed able to coordinate and scale with the number of action dimensions or action choices per dimension. This can be best seen when looking at the performance of sequential agent Q learning with the green learning curve. In comparison, a single policy can learn about interactions, but its performance worsens when increasing the action space size, which can be seen for the blue learning curve representing the performance of DDQN. DDQN is a classic and the original approach to DAC and thus a relevant baseline to beat. Our independent factorized policy baseline fails to coordinate optimally and is outperformed under any action space configuration. We can see this for the orange learning curve of independent Q learning. Simplified sequential DQN is another version of sequential policies that was proposed by prior work. For more details, please have a look at our paper or talk to us during the conference. To summarize, in our work we have shown sequential policies can be an effective approach for coupled action dimensions with importance differences in DAC. However, this study was only the first step and we yet need to do more experiments. In the first place, we need to evaluate sequential policies in real-world settings. And we should compare against more advanced multi-agent reinforcement learning baselines. There is also plenty of room for future work, such as extending the approach to advanced communication schemes, for example learned message passing, and combining it with centralized training schemes like value function factorization. We are looking forward to discuss our results and ideas at this year's AUTOML conference.